Hello, this is the second part of chapter 15, dealing with the objectives. And this set of objectives are mainly what the student is expected to know. And so I'm going to share my PowerPoint with the students so that you know exactly what this chapter entitles to when you are studying the particular chapter and the highlights of important information that a student must know. First and foremost, at the end of chemical kinetics, chapter number 14, we found out that the chemical reactions are reversible, especially when considering under elementary conditions. At that time, we wrote that the rate of the forward reaction is equal to the specific rate of the forward reaction times the product of the concentration of the reactant raised to its stoichiometric mole exponent. Now, the same concept we are going to use and apply it to any type of chemical reaction. Because in chapter 4, the mechanism gives us a kinetic data for a given reaction and the possible mechanism that can be applied to that particular reaction. So in chapter 15, we try to understand and remember that chemical reactions under submicroscopic levels are reversible. They are dynamic. The expression for such reactions is the equilibrium constant K is the ratio of the products over the concentration of the reactants. The equilibrium constant, depending upon the nature of the reaction, can be written either in terms of concentration or in terms of partial pressures. Remembering that partial pressure is related to the concentration for the chemical reactants and products, we can then correlate the equilibrium constant at concentration level or in terms of partial pressure. Once we do that, we get the values for the equilibrium constants, and the values can be used to predict whether the reaction will be a reactant or a product favored at equilibrium. Now, should the reaction not be in equilibrium, then we write the same expression but call it the reaction coefficient. There are three cases for the reaction coefficient. One, the reaction coefficient is less than the equilibrium constant, K, in which case it tells us that the amount of product formed is very little and the amount of reactants breaking down or getting converted is much higher, smaller, so that we have a large amount of the reactant that is present. And therefore, the reaction will tend to move towards the right in order to achieve equilibrium, thereby decreasing the concentration of the reactant and increasing the concentration of the product. Now, on the other hand, if the reaction coefficient is greater than K, then it tells you that a large amount of the product has formed, and in order to attain equilibrium, the products will break down and go back and get converted back to the reactants and then approach equilibrium. And should Q be equal to K, in that case, we find that the reaction is in equilibrium. Now, we also said that there is a relation between Kc and Kp. Now, for Kp is for gas, partial pressure for gas, and we know that the partial pressure depends upon the temperature and the gas constant R. And so we have to find out the partial pressures for each of the reactants, and then find out, determine what is the number of the terms that contain RT, the gas constant times the temperature, noting that the equilibrium constant remains constant at a given temperature. Once we get that, then we should be able to write, generally, if concentrations of equilibrium concentrations of reactants and products are given, then we can calculate the equilibrium constant. If the equilibrium constant is given and if the concentration of one reactant or product is given, then also you should be able to calculate the equilibrium constant K. Same thing, if the concentrations or pressures are given, then you should be able to use the concentrations to calculate the equilibrium constant for the reaction. Not only that, you should also be able to predict whether it's going to the reactant side or the product side at equilibrium. Lastly, you should be able to manipulate chemical equilibrium expressions for multiple reactions in such a way as to get a specific expression for a given required reaction, and then calculate the equilibrium constant values that are there. And lastly, you will have to find out how a system in equilibrium will respond when a stress is applied, remembering that the stresses for equilibrium reactions can be pressure, volume, temperature, and of course the nature of the products, or the amounts of the products or reactants that is there. So all these you are expected to know and predict by looking and manipulating the reactions that are there. Now, the rationalization for this particular study of this topic. This topic introduces students to reactions at some microscopic levels, and 2 reactions at some microscopic levels are reversible and dynamic. The rates of the forward reaction equals the rate of the reverse reactions, and the concentrations for each of these reactions or the partial pressures must be raised to the stoichiometric mole coefficients for it as exponents in order to calculate the equilibrium constant, a constant that is there. Then once you know the equilibrium constant K, knowing that it will only vary with temperature, students should be able to predict whether the reaction is reactant favored or product favored. And finally, use different K values for different reactions and determine the equilibrium constant for a required equation that is there. And lastly, students should be able to predict what would happen if conditions are changed and the reactions, and explain how biochemical reactions and environmental reactions occur and how we can use those concepts to detoxify or enhance the reaction product that is there. And with that, I'm going to stop the share.